Hello everybody, welcome to chapter 6. This chapter we're going to be talking about the normal distribution. And this is going to form the basis for the rest of everything that we do in the following chapters 7, 8, and 9 for the rest of the course. Now what we've done so far when it comes to dealing with normal distributions is that we looked at the normal distribution in the context of a data distribution. That is, when we found a curve and when we found a histogram and we looked at its shape, we were able to tell possibly something about that shape. What we're going to talk about here in the normal distribution is the idea of what happens, what situations would we expect to find a normal distribution, and how would we find the probabilities associated with that normal distribution. So we're reaching back a little bit to our probability and to our graphing and distribution areas, as well as finding the mean and standard deviation, all become involved in this process. So the very first thing we want to do is introduce the idea of normally distributed variables. What does that even mean? Well, first of all normally distributed variables, when we talk about continuous variables, remember a continuous variable is a variable that can take on a value anywhere over a continuum on the number line. Not just whole numbers, but numbers in between. But even on whole number types of quantities, we can treat them as continuous quantities, and they have a certain property when we do that. They form often what's called a density curve, and a density curve is always on or above the horizontal axis, and the total area of the density curve, and therefore the total probability associated with all the events that could happen in that density curve are equal to 1. That is 100%. So we picture a density curve as being a curve that might represent some sort of outcome from a histogram, where we have a total area under that curve, that is all the possible probabilities that could occur from events that occur within that particular histogram, and that has a total area of 1. That's sort of an interesting idea right here. Let's see what that takes us. Well, for a variable with a density curve, the percentage of all possible observations of the variable that lie within a specified range equals, at least approximately, the corresponding area under the density curve. And this is our critical point right here. We can express that as a percentage. Right? So what we mean is that if we're looking at our density curve right here and we find a value C, let's say, that gives us a area under that curve, right? The percentage of all the possible observations of the variable that lie to the left of C will equal the percentage, will equal that area as a percentage. Now, we can also put it in a couple different ways. The percentage of all the possible observations that lie to the right of a certain area would also be expressed as a percentage, and we're saying that the area to the right would also be expressed as a percentage equal to the area to the right of D. And finally, if we wanted to find two different values, right, we would say the possible of all observations of that variable lie between two numbers A and B when we express that area as a percentage. Remember, this is a density curve. It's formed by taking probabilities. Now, for a normally distributed variable, we state that our variable, when we look at its distribution, its density curve, it will have a normal distribution. Remember that was the kind of curve that was shaped like a bell. That is, it had a high center value and it was equally distributed on either side of that mean. Let's take a look at a specific example. Height, human height, is actually a very good example of the kind of variable that would normally be distributed. That is, there's many variables that determine height, both nutrition, both genetics, environment, exercise, a whole range of things that might determine height. So it is a perfect candidate for a variable. So what do we mean? Well, if we were to look at the frequencies, let's say that we took a sample of 3,264 adults and we looked at their heights. Well, we looked at the frequency, right, between 56 and 57. It's a continuous variable, right? Somebody could be somewhere between those two, 57, 58, 58 to 59, and so on. So we go by 1 inch increments right here. And we find that the number of our persons in the sample are highest right here in the middle at 559, but then decrease pretty equally on either side of those. So what do? Well, we go to the relative frequency, and that relative frequency represents our percentage. Why? Well, look at what happens. All of the relative frequencies, 3 divided by 3,264 gives us 0.09. 6 divided by 3,264 gives us 0.018, and so on down the list. Each one of these values represents our, let me get my pointer out. Each one of these values here represents a probability, right? So we could almost think of it as saying, oh, our probability of finding somebody with a height at random in this sample between 62 and 63 inches would be equivalent to saying 382 out of 3,264. That is 0.1170, right? That's an 11.7% chance. So what do? If we added up all these percentages here on the right, we get 1.00. That's equivalent to saying that the area under the curve is 1.00. And if we were to look at our histogram from this data and we superimpose our curve on there, we get this nice, beautiful, normal curve going around where the mean is 64 inches in height. Here we are at the mean. And the standard deviation is 2.4 inches in height, right? So we go 2.4 inches to the right or 2.4 inches to the left, and we're going to find one standard deviation to the left or the right. So if we said, well, what was our probability here? We could actually say, well, the probability of finding somebody between 67 and 68 inches would be, let's see, 1 times 0.0735. That's actually the height right here. Notice on our vertical axis. That height right there represents the probability, at least approximately, right? We get a little bit above under this curve and a little bit below under this curve, but it's like that rectangle right there represents our area under the curve, and we would say that this represents our probability of getting somebody who is between 67 and 68 inches out of our sample, 0.0735. Well, that's interesting enough for us to be able to pursue this, because a lot of variables, it turns out, have exactly this same kind of property, and we could plot their values measurably on a histogram just like this one and get a nice normal curve and use that to help us find probabilities of values just like that one. So for any normally distributed variable, the percentage of all the possible observations that lie within a specified range equals the corresponding area associated under the normal curve, and we express that as a percentage. This result holds approximately for a variable that is approximately normally distributed, right? So if we could find a variable that is normally distributed, we're actually really, really good, right? Now, let's take it one step further. The other thing we need to know is that whenever we're talking about these normal distributions, we have what we call the standard normal distribution. The standard normal distribution is useful on a number of levels. First of all, a normally distributed variable has a mean of 0 and a standard deviation of 1. That makes it really, really easy to understand what the values are under this curve. Its associated normal curve is called the standard normal curve, right? And so why do we even care about this one, right? Don't we have all kinds of samples that have different means, different standard deviations, and so on? Well, yes, that's true. But what we do is we can standardize each of those variables by using what's called a z value, right? The standardized version says take the z value, and we talked about this as a means of determining how far, let's say, our actors were from their mean age, right, according to gender. And we said z was equal to the x variable minus the mean over the standard deviation. When we do that, we get what's called a standard score, the z-score. And that has a variable that's equal to the z value we would see under a standard normal distribution. Why? Well, look at the different curves that we could have. We could have a mean at -2, or a mean at 9, or a mean at 3, right? And all of these normal curves, depending on our variable, might have different distributions, but they're all normal distributions. But the nice thing is that if we go through and we look at the z-scores that we get for the variables, right, the z-scores would be equal under the standard normal distribution. That is, if we were to pick a value of x, we could pick a value of x in such a way that if we subtracted the mean of this distribution over here in pink, right, if we took that variable value x minus 9, which is the mean, over 2, the standard deviation, it is potentially possible for us to find a value of x in this red distribution that when we subtracted it from 3 and divided by 1/2, we would get the same value as in this green distribution with a mean of -2 and a standard deviation of 1. We just take the difference between the x value and the mean and divide it by the standard deviation. And every single time we get a z value that is laid out here under this standard normal curve. And so we can use that if we know something about the probabilities of the standard normal curve to get probabilities associated with any of these other curves. And that's pretty neat. Right? So our idea right here is this. We're going to be finding percentages of areas under the curve from any other distribution, from whatever normal curve distribution we have. And through the means of this z-score, the standard score, find the area under the standard normal distribution curve by use of a table. And that's our goal. How do we find those equal areas? And it is by means of this z-value. So we'll go through an example where we have to do that. Let's consider M&Ms, right? And according to the M&Ms website, about 14% of milk chocolate M&Ms are yellow. So now, does this mean that we're guaranteed to have 14% of the candies in each bag be yellow? Should we be concerned if there's only 10% of them yellow? What if all of the M&Ms are yellow? At what point would you suspect that the advertised proportion is incorrect, right? That this claim is poorly made, and it was just an estimate some guy made just because, well, hey, it sounded like a good advertising ploy. Well, we'll discuss these questions, and we're going to explore it with a bag of M&Ms. Now, you can get your own bag of M&Ms and follow along. I'm going to show you what I did with my bag of M&Ms here, and we also have a virtual bag of M&Ms that we can use for our samples as well. All right, so my bag of M&Ms, I got a bag of M&Ms that contained 52 candies in them. All right, so I got 52 of those candies, and when I counted them out, I found that 6 of those 52 candies were yellow. So the actual sample proportion of the yellow candies for this bag is 6 divided by 52.1154. All right, so what I want to know is that according to the site, right, we're with that 14%, right, of our M&Ms should be good. Well, we're told then that we have a mean distribution of all of our M&Ms, of yellow M&Ms, where the mean is 14% and the standard deviation is 5%. I got that from a research website that actually went through and researched M&Ms. It's sort of interesting that somebody had time to research M&Ms, but it's a good numbers game. So what would we do to figure out what percentage of bags might have something less than 0.1154, right? 6/52 of that bag full of M&Ms. Well, here's what we do. We go to, what we can do is we can look up this information. First of all, we're going to find our z-score. The way we deal with the z-score right here is this. We say take the z-value. And let me just highlight this right here for you guys right here so you can see my calculation. We're going to take our z-value to be the difference between x and the mean, right? So we stated in our situation, right, it was x minus the mean divided by the standard deviation. Well, right here, our population mean being 14%, but our actual bags value right here being 0.1154. So we take that difference and we divide it by 0.05. You can pause the presentation and check that out for yourself. We get negative 0.492. So what we do is we use this value with correct to the nearest hundredth, 0.49. And what we're going to do is we're going to look up the probability associated with this z-score on the table. All right, so how do we do that? Well, this is in Appendix 1 of your textbook. If you go to Appendix 1, you'll find Table 2, areas under the standard normal curve. And the way it works is this. The z-score is found along this column. Now, we actually ended up with a negative z-score, so that means that when z is negative, that means that we're picking values that are to the left of 0 right here on the number line. So we go to this part of the table. There's another part of the table where if z is positive, we're to the right. Right? So if z is positive over here, that's where we would look. But we're on the left-right side, so we're going to go to the left table, and we're going to say, all right, how do we find z equals negative 0.49? Well, we have two digits going on here. The first is the tenths. This z-score column gives us the tenths. So we follow this along until we get to the point negative 0.4. And then we go for the hundredths digit along the top row up here. So negative 0.9, right here. We think of it this way. This is negative 0.40 as our row. And then the 0.09 as our column, right? Because when we add these two up, of course, we get negative 0.049 right there. All right, so we look to see where these numbers cross, and here it is. Right here at this point, we find 0.3121. 0.3121. We say this is our probability under the curve of finding a bag less than 0.49. So if we were looking at the area under the curve right here, the area under the curve that we're looking at for our z-score is 0.3121. So what does that mean to us? Well, for our bag of M&Ms, that means that we would find, according to the z-score, the percentage of bags with plain milk chocolate items that will have a lower percentage of yellow candies than your bag would be 31.21%. All right. So that's how we go about finding a normal distribution.